antiderivative. That's what we're doing today. So what would that mean to you, taking the antiderivative? Well, that's finding whatever f of x was that gives us a certain derivative. So we're going to undo the process. So let's just kind of think through it. What if I knew that the derivative was 2x minus 3? What could I have as my original function? Well, we know if we got 2x, then that had to come from x squared, right? Because we would have taken the exponent down and then subtracted 1 from there. To get just a negative 3, that would have came from negative 3x. But couldn't I have had basically anything at the end? I mean, this could have been plus 2, because the derivative of 2 is 0. Could have been plus 20 for all I know. Could have been plus 28. So the idea of taking the antiderivative is you are finding a antiderivative. There are millions of possibilities because of that constant. So let's look at another one, and then we're going to get to the nitty-gritty of it. So we're looking for the original function. If my derivative was, let's say, three x squared plus 4x plus 2. Well, what would the original have been? Well, to get 3x squared, that would come from x cubed. To get 4x, gosh, that would have been 2x squared. This would have been 2x plus something. So C stands for constant, so plus constant. So let's think about how we take a derivative, and let's get a more formal process than just kind of guessing. If we had to explain to somebody how to find the derivative of a polynomial, well, the first thing I would do is multiply the coefficient by the exponent of that term. And then what else do you have to do when it's a polynomial? Well, you would have to decrease the exponent by 1. So the opposite of those actions would be, so if we're going backwards, the opposite of decreasing by 1 is to increase the exponent by 1. And the opposite of multiplying by the exponent would be to divide the coefficient by the new exponent. Let's see if that works on the ones we're looking at. So if I follow those rules, increase the exponent by 1, then divide by the new exponent. Let's see if that applies. So if I increase the exponent by 1, I would get x cubed divided by the new exponent. Increase the exponent by 1, which would turn that into a 2, divide by the new exponent. Increase the exponent by 1. Well, if there wasn't anything there to begin with, that gives me an x to the 1, divide by the new exponent. And then because of the constant, we are always going to have a plus c. Does that match up? 3x cubed divided by 3? Yup. 4x squared divided by 2? 2x divided by 1? It works. So in the notes, it talks about here about that the problem we would foresee is that we have to have that constant in there. So I'm going to just jot that down because we talked about it. You don't know what the constant might have been. This notation, this large S, this is the notation for the antiderivative. So I would say if I'm taking the antiderivative of f prime of x, that's going to give me my original function plus some c, constant. So we don't want to ever forget the c. So let's try it. 3x squared, oh, that's very similar to the one I did, so pretty easy. 3x, add 1 to the exponent, divide by the new exponent. 2x squared, divide by the new exponent. This is going to be 3x to the 1, divide by the new exponent, plus c. So I get x cubed plus x squared plus 3x plus c. The nice thing about taking antiderivatives, it's kind of like factoring, you could always check your answer. Take the derivative. Do you get what was in the parentheses? 3x squared, 2x, and 3. You do. Let's see. Oh, that's ugly. Maybe I should clean it up a little bit. So let's clean that up before we start. X cubed divided by x is x squared. 2x divided by x is 2. And then that's negative 4 divided by x. Well, I can rewrite that as 4x to the negative 1. dx. And we always have this dx because remember the dy dx, this is just saying x is our variable that we're taking the antiderivative of. So we're going to add 1 to the exponent. Divide by the new exponent. Add 1 to the exponent. Divide by the new exponent. But here we run into a problem. If I add 1 to the exponent here, I get 0. So that doesn't work. So let me think back on if I knew something that if I took the derivative of it, I got 1 over x, or 4 over x. Well, let's just stick with the 1 over x. What can I take the derivative of? Let's come off to the side. That would give me 1 over x. So what would f of x be that the derivative would be 1 over x. Well, it's actually natural log. So anytime when you've got, like this was 4 over x actually, you can't use the add 1 to the exponent because you get x to the 0, which then makes you divide by 0, which makes no sense whatsoever. This is going to end up giving you natural log x. Uh-oh, I don't know a product rule for this. How about let's multiply it out? That'd be 2x squared, and then I'd have 4x and a negative 3x, so the middle term would be an x. 2 times negative 3 is negative 6. Now we can take the antiderivative. So add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Increase the exponent, divide by the new exponent. Then we just have to clean it up. That's 2/3 x cubed plus 1/2 x squared minus 6x plus c. Ooh, dividing by a square root. Yuck. Oh, let's rewrite it. That's 2x to the negative 1/2. Now we can apply the rule. Add 1 to the exponent gives me a positive 1/2, and then divide by the new exponent. Well, if I'm dividing by 1/2, that's the same as multiplying by a 2. So this would give me 4. X to the 1/2 is the square root of x plus c. Now what would we do if we were trying to find the antiderivative of cosine? So you have to think to yourself, what can I take the derivative of to get cosine back? Easy. The derivative of sine is cosine. What would give me sine? Ooh, the derivative of cosine is negative sine, so this would have to be negative cosine. So what about 2 sine x? Well, the antiderivative of sine is going to be negative cosine, so it's going to give me negative 2 cosine x. And the antiderivative of cosine is sine. And we have a plus c. Oh, t squared minus sine t. So this is going to have the quotient, power rule, anti-power rule at that, minus the antiderivative of sine was negative cosine, plus c. I can make that prettier. 1/3 t cubed plus cosine t. (4x minus 3 cosine x). So the anti-power rule, add 1 to the exponent, divide by the new exponent, minus 3 times the antiderivative of cosine is sine, And 4 divided by 2 is 2. So 2x squared minus 3 sine x plus c. Think I would rewrite that as x to the 1/2 before I start. So this is going to be x to the 1/2 plus sine x dx. Add 1 to the exponent. Divide by the new exponent. Antiderivative sine is negative cosine plus c. Now dividing by 3/2 is the same as multiplying by 2/3. Now sometimes they give us a little bit more information, which makes it awfully helpful. This one gives me information about the second derivative, the first derivative, and the original function. And we're trying to find f of x. So since we're working backwards, let's start with the second derivative and work back all the way to the original. So the second derivative is 2. So if we take the antiderivative of that, I'm going to take the antiderivative of this side too, dx, with respect to x. And that's going to give me 2x plus some c. That means that f prime is 2x plus c. Well, they tell me something about f prime. They say f prime of 2 is 5. So if I plug in 2, I can actually find out what that constant is, and so it's no longer a mystery. So now I know what f prime is. It's 2x plus 1. So could I use that to help me find f of x? Well, sure, I just need to take the antiderivative of that. So the antiderivative of 2x plus 1 is going to be 2x squared over 2 plus 1x to the 1 divided by 1 plus another constant. Now this is a different constant. It may not be 1. Could it be? Well, sure. I don't know. I just know that now f of x is x squared plus x plus some constant c. Not necessarily the same c that we had there. That was just a placeholder. But what do we know? I know that f of 2 equals 10. So f of 2 equals 2 squared plus 2 plus c, and that's going to be equivalent to 10. So that's 4 plus 2, that's 6 plus c is 10. So this constant is 4. So that means f of x is x squared plus x plus 4. Try one more. Second derivative is x to the negative 3/2. So to find f prime, that's going to be the antiderivative. Why does that look funny, Allison? Antiderivative of x to the negative 3/2 dx. Which means I need to add 1 to the exponent. Makes it a makes it still negative, sorry, divided by the new exponent plus some c. So f prime is dividing by negative 1/2 is the same as multiplying by negative 2. And x to the negative 1/2 would be the same as dividing by square root of x plus some constant c. Now, we're given some information. We're given that f prime of 4 is 2. So f prime of 4 means I need to plug in 4 for my x. And that should be 2. Well, square root of 4 is 2. So this is negative 2 over 2, which is negative 1. Plus some constant is 2. So this c is 3. That tells me that f prime is, and I'm going to write it back with that exponent, plus c, which we found to be 3. Now the reason I wrote it back as a fractional exponent is because to find f of x, I need to take the antiderivative of that. So we're going to add 1 to the exponent. Makes it a positive 1/2. Divide by the new exponent. It's going to be 3x to the 1 divided by the new exponent plus another constant c. Well, dividing by 1/2 is the same as multiplying by 2. So this is negative 4 x to the 1/2, or square root of x, plus 3x plus some constant. And they give us some information. They tell you that when f of 0 is 0. So f of 0 would be negative 4 square root of 0, 3 times 0 plus c, which means c has to be 0. So I'm able to find that f of x equals, ran out of room, f of x equals negative 4 square root of x plus 3x plus 0. Now, how can we apply this? Well, what if I was given some information and that they told me about the rate of change? So we have an evergreen nursery selling a shrub, and the growth rate during its first 6 years is approximated by this function. Differential equation just means this is the derivative. They tell us the seedlings are 12 centimeters tall when planted at time 0. That means that the original height at 0 is 12. We've got an initial condition, which is awesome. Then it says to find the value of the differential equation above when time is 3. In other words, to figure out dH dt at t equals 3. So we're just going to plug 3 in. 1.5 times 3 is 4.5 plus 5 is 9.5. And this is the rate of change, the rate that it's growing. So that's centimeters per time, which is per year. So what does this mean? at time 3, so 3 years after planting, the height of the shrub is it increasing or decreasing? That's positive, so it is increasing at 9.5 centimeters per year. Now it asks us to find an equation for h of t. So we had dh dt, 1.5 t plus 5. So to find the original function, I need to take the antiderivative. Shoot, shoot, with respect to t. So this means I'm going to be finding my original function. So I need to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, plus some constant c. Well, half of 0.5 is 0.75. Now, do we know anything to help us find that constant? Oh, we know that at time 0, the height was 12. So if I plug in zeros in for my times, I get a 12. Oh, that means c is 12. So h of t equals 0.75 t squared plus 5t plus 12. Now it also says to determine how tall the shrubs are when they're sold. Let me look back at the problem. When are they sold? They sell the shrub after 6 years. So I need to find the height after 6 years. So here's part of the answer. Now I need to find the height after 6 years. And I'm going to use my calculator. Plus 30. And I got 69. And the height was measured in centimeters. How could this help us with particle motion? Well, what if I know my velocity equation and I want to find out acceleration and position? Well, how are they related? Let's think. Velocity, let's rewrite that as t to the negative 1/2. Acceleration is the derivative of velocity. Which would be negative 1/2 t to the negative 3/2. And if I want to find my acceleration at time 9, I'm going to just plug in 9. Let's see. That's 1 over 9 to the 3/2, which is going to be the square root of 9 cubed. So that's 1 over 27. So I get negative 1 over 54. What about the position at time 9? 1 m of velocity. And the position is the level above that. So I need to find the antiderivative of velocity. That would give me position. So I'm going to add 1 to the exponent and then divide by the new exponent, and I'm not going to forget my c. So dividing by 1/2 is the same as multiplying by 2. That really means the square root of t. Gosh, I need some information to be able to find that constant. Oh, at time 1, the position is 4. That means P of 1 is 4. So if I plug in 1, my output should be 4. So that's 2 plus C is 4. So C is 2. So let's rewrite the position function. 2 square roots of t plus c, which we now know is 2. And it says, what is the position at time 9? So square root of 9 is 3. 6 plus 2 is 8.